very linked subjects because, well, a sector is a fraction of a circle. As such, we're going to be looking at them both together now. To start off with, just with regular old circles, these are going to have a radius, which is a length from its center to its edge, this being a straight line. And if you had a line going all the way through, that would be the diameter. The radius is half the diameter. If you're given the diameter in such a question, you may wish to halve it first and make sure that you do, if it is necessary. The area of this circle, therefore, you may be familiar, is found using pi r squared. But pi is a constant you can find on your calculator, and then r is just whatever number they've given you here, squared. So if this was a 5, you would do pi times 5 squared. As for the circumference, that's the length all the way around the edge. This is found by 2 pi r, or alternatively, pi times the diameter. But again, it's probably more common practice to use the radius just because it does appear in both formulas. With this in mind then, if we're just to turn to a different circle, let's say this is a circle with a radius of 8. Now if we wanted to find the area of this circle, we would therefore do pi times 8 squared, and depending on whether or not the question asked for an exact form or given to however many decimal places, if they wanted an exact form, you would do 64 pi, but if they wanted decimal places, you could say that that's going to be like 201.06 to 2 decimal places, or if they wanted 3 significant figures, just 201, because it's 1, 2, 3 sig fig, and the 0, which is the 4th significant figure, rounds down. If they wanted the circumference, then that's going to be 2 pi times 8, which is then either going to be 16 pi, or, again, if you're wanting to do this to, let's say, 2 decimal places, then that's going to be about 50.27, or 50.3 if you want 3 significant figures. We can use these to also get from the area to the circumference, however, even if we don't know what the radius is. Let's say that we knew the area first. We knew that the area of the circle was 20. From this, how do you get the circumference? Well, if the area equals 20, then that 20 will equal the pi r squared. Rearranging this, you'll get r squared equals 20 over pi, and so r on its own is the square root of that. Once you have that value in your calculator, I would suggest that you keep it in the calculator with all its significant figures, or all its decimal places, in the answer button if needs be, just because it's going to increase accuracy. To then get the circumference, you'll just say, okay, it's 2 pi times whatever that answer was. So in our case, that's going to give you approximately 15.85. Again, to 2 decimal places. For a sector, though, as I say, that's just a section of a circle. Regarding its area, if we were to continue this all the way around, yes, it would be a full circle, so its area will be related to what it would have been as a full circle. But instead what we're going to say is that it's the angle which we're representing here with the Greek letter theta. You don't have to, but that's just a potentially more traditional mathematical way of looking at it. So it's theta out of 360, because that's how many degrees there would be in a full circle. So it's theta out of 360, and then again times that pi r squared. So if the radius was 5, as kind of suggested up here with this one, and the angle, let's say, was 75, you'd have 75 over 360 times pi times 5 squared. For the arc, no longer the circumference. Circumference is only all the way around. For the arc, that's just the curved bit here. Again, it's going to be a fraction of what the full circumference would have been. Again, that fraction is going to be theta over 360, and then times 2 pi r. This isn't all the way around, no, however, as in for the sector. That's not the full perimeter. Now we have two additional radii added on, and they are both the radius because they're both the edge to what the centre of the circle would have been. So for the whole perimeter of this sector, it's going to be the arc you may have just worked up here, and then add two lots of r. Given an example here then, let's say that this radius, actually I'm going to use similar numbers, let's say this is a radius of 8, and then I'll use that 75 I just suggested. For the area therefore, we're going to have 75 over 360 times pi times 8 squared, which again, as why a question may say exact form, is because your calculator will inherently round if it's a long decimal. Even if it seems like it's being really thorough, it's still rounding off at some point. So to be exact, you leave it in terms of pi, you leave it as the fraction in any kind of context. Or so in this case, that fraction would be 40 over 3 pi, or if you preferred it as a decimal, again, two decimal places, 41.8. 9, and if they're given a unit of length, it'll be like that squared, so centimetre squared, metre squared, so forth. For the arc, similarly, we're going to have that 75 over 360, and then that's going to be times by 2 times pi times the 8, plugging in the calculator. This, so that was 75 over 360 times by 2 pi times 8. This is going to give you 10 over 3 pi, or alternatively 10.47. For the perimeter, you then have this arc length, you're just adding two lots of the radius on. If this is 8, this is 8. Adding onto that, that's just going to make the perimeter 18.47. Okay. If we're happy with that, let's see how we get along with a question of our own. Again, I'm going to get you to do an example of both, one of a circle and one of a sector. To start off with the circle, if we have an area of 50, what would the circumference be? And with the sector, so the area squared, with the sector, if the angle here is now 60, and we've also introduced an extra arc here. I am adding extra details. Let's just see how we get along with those. To make this a shaded area here, if you need to just double check on how you work out shaded areas of compound shapes, check out the video on that as well. This length here specifically is then going to be 5, and this length here is going to be 3. Can you work out the perimeter of the shaded region? Count what the perimeter of the shaded region is going to be. So yes, that is, as I said, different to what we have been doing, but it is using the same principles. And then up here, we were after that circumference. Have a go, pause the video, just have a think about it, and then when you're ready, press play again and we can compare answers. Alright, so for the circle, it's kind of like what we were doing previously, where if we can work out the radius first, the radius is going to be 50 divided by pi and square rooted, just making r the subject of the area formula. You take the pi underneath and then get rid of the square root. Keep that value in your calculator, and then if we just put that as 2 pi times that answer, you should, if we're rounding to two decimal places for instance, have got a circumference of approximately 25.07 centimeters. As for this sector bit here, the perimeter of this shaded bit is going to be the straight line between here and here, and between here and here, then this curve and this curve. If this here is a 3, this 2 is going to be a 3. So already we've got 6 to add on to our perimeter. Then after that, it's going to be this big arc here, also adding the smaller arc. Now to work out the big arc, so we're using this arc formula here, your theta is 60, so 60 over 360 times 2 pi. And for this big one, the radius is a combined 8, because again it's from this curve, this edge, to the centre all the way. So 60 over 360 times 2 pi times 8. And then for the smaller one, it'll be 60 over 360 times 2 pi times 5. Put this all together, add together with the 3, you should get a perimeter that, again, let's just say 2 decimal places, is going to be approximately 19.61. And yes, say those were centimetres. If we're all right with that, let's try an actual question. Now, once again, this question is going to be using concepts we haven't necessarily talked about so far, as well as looking at the shaded region made by compound shapes. This is also going to be looking at some trigonometry. So if you're not entirely happy with trigonometry, I suggest you just go watch that video as well. Even so, the reason I want to look at this here is it shows that within exam questions, the question may not solely be about a sector in isolation. It's going to require you to use different concepts in conjunction, and this is just a practice of that to make it clear that this is what we would do if faced with this in a paper itself. Right, so just looking at the diagram now. We're starting with a quadrilateral OABC, within which is then the sector of a circle. The centre of which is O, so this angle here, the 120, that would be our theta, and OA is our radius. This also makes OC our radius, so we can just label that as 10 metres as well. BA is in a tangent to the circle at point A, and BC is a tangent to the circle at point C. We may know from circle theorems, yet another concept I'll suggest we make sure we're happy with, that a tangent and a radius of a circle meet each other at 90 degrees. So this will be 90 here, and this will be 90 here. Just making some annotations, just so we have them, we're aware of all the information that we can make use of from the start. Once again, just acknowledging the angle is 120 degrees, and then it says calculate the area of the shaded region. So if we can get the area of the entire quadrilateral, get the area of the sector, we can then take them away from each other to get that shaded region. Problem is, how do we get the area of this quadrilateral? It's not a square, it's not a rectangle. We can't just do like the 10 times the 10. We'll have to find some other way. Well, if we were to just split this down the middle here in what's meant to be a straight line, we make 2 right-angled triangles, where this now is going to be 60 degrees on each side. Just looking at the left-hand side in isolation, therefore, if we just wanted to also tip it slightly so that 10 is a base, we have our 60 degrees here, we have our 10 meters here, and this is our BA that we're trying to work out. Well, say it's a right angle triangle, we have an angle, 2 sides are involved, we'll be using our trigonometry. Labeling the sides of this triangle, this over here, BO, is going to be our hypotenuse because it's the longest length, it's the one not touching the right angle. The 10 is in our adjacent because it's also touching the 60, and the BA is our opposite. This is going to involve the opposite in the adjacent, so we'll be using tan, TOA from the SOHCAHTOA acronym. So tan 60 is going to equal this BA that we're after over 10. And if we just want to rearrange this, we'd be bringing the 10 up onto the other side, so the BA is no longer being divided by it. Put this into your calculator, and you would get a value of 10 root 3. You might as well, for now, keep it in this exact form rather than the decimal, because we're going to be going on to work out more values after this. As I said before, try to keep the exact value in your calculator. Now that we know that this is going to be the height here, we can work out the area of this triangle. That's going to be half base times height. So half times a base of 10 times a height of 10 root 3. Well, 10 times 10 is going to be 100, half of that is 50, so the area of this is going to be 50 root 3. For the other side, because we also need to make that part of the quadrilateral, that's going to be the exact same thing, because again it's a right angle triangle, where this side, the adjacent, is 10, this angle is 60, and the side we're trying to find is the opposite. So that's going to end up being another length BC of 10 root 3, another area in total of 50 root 3. Therefore, the area of quadrilateral OABC is going to be that 50 root 3 add 50 root 3, bringing us back to 100 times root 3. So now we have the quadrilateral. From here, we can get the sector. So as before, the area of the sector is going to be the angle over 360. So this is 120 over 360. Then times by pi times the radius, which was 10 squared. Plugging this into your calculator, you should get a area of 100 over 3 pi. Yeah, let's just keep them in exact values as before. I know the answer at the end is saying in 3 significant figures. But again, that's more for the final answer. You don't have to adhere to that rule in any other stage of your working. So here we have the quadrilateral, we have the sector. Shaded region now will just have us taking them away from each other. So 100 root 3 minus 100 over 3 pi. Put this all back into your calculator, and you at last will get a shaded region of, to 3 significant figures, 68.5 meters squared.